is there a secret fourth kind of matter besides solid, liquid, and gas? Yes, there is. It's called chained matter, and it actually helps us understand the origin of life. Let's dive in. Hey guys, welcome to the channel. My name is Reese. I used to teach tech ethics at MIT, and now I'm running this series on how everything evolved, where I kind of share some learnings from a decade of research I've done, including these 20,000 note cards on all these different subjects. And so today, here's our little timeline, and we're chatting about right here, the origin of life. What a beautiful and crazy moment. Why do we care about the origin of life? It happened 4 billion years ago. Well, there are 3 big reasons to care about it. The first is it's fascinating. To go from abiotic system to a biotic system, that's pretty cool. The second big reason, it helps us understand these origin processes. So if we understand the origin of life, we can then understand the origin of sapiens, or the origin of the Industrial Revolution, or the origin of something like AI. There are kind of shared patterns among origin processes that we can apply to our learnings over time. And the third big reason is because by understanding the origin of life, we get kind of a gears level understanding of biology, chemistry, biochemistry, and that'll help us understand life as a whole. Okay, so let's do it. Let's understand the origin of life. And so today we're going to talk about 3 things. First, we're going to talk about these 3 first kinds of matter, solid, liquid, and gas. Then we're going to talk about chained matter. And then finally, we're going to talk about how chained matter came to be on Earth. Okay, so what are the 3 kinds of matter? Well, we have gas, we have solid, and then we have liquid. And those kinds of matter are actually, like when you look at the universe as a whole, that's where all the matter is. Yes, there's a bunch of this other matter called plasma, which is in all the stars and stuff, and that's just like atoms that are ionized, where the electrons are shot off of them. So there's tons of plasma, but mostly those other 3 kinds of matter, the main 3, there is so much gas in the world. There's, gas is what mostly exists. And here's a representation of gas with these beautiful snatoms. And you can see here that these are H2. So this is a bunch of hydrogen gas. And we know with gas, what it does is it goes beep, 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 and it bounces around where I'm in a room of gas, 80% nitrogen, 20% oxygen. That's the atmosphere of the Earth. And so gas expands to fill its container, and we kind of know that well, and it bounces around all fast. And so this little H2 atoms are gas. Then we have a solid, and solids are the next most common type of matter. So you can imagine a lot of the solar system, there's a bunch of these gas giants, but they all have these solid cores. And so solids, happen at a less temperature. And here's an example of a solid. This is a silicate. It's essentially a rock, like a rock like this rock. And so a solid, what it does is, they form into these crystalline structures. And so this is Si, these represent silicon, and this represents oxygen. And they form these long crystal structures, turning into something like this, which has, billions and billions of atoms formed into this crystal structure. So that's solid. And then finally, we have a liquid. There aren't that many liquids in the universe or in our galaxy or in our solar system. And so in our solar system, there's roughly 25 oceans worth of liquid in our solar system. There's our ocean, and then there's some on some random moons around Jupiter and Saturn, which is why we're going there to see if there's life. And so liquids almost always take the form of water. So these H2O molecules will form a liquid like this one. I don't want to pour this on my desk on accident. I can drink a little bit though. My parched throat.
Nice.
Liquids, obviously, they fill up their container like so. And so these are the 3 kinds of matter. We have our gas over here, lots and lots of gas in the world, high temperature, low pressure. And then we have our solids, where we have low temperature and higher pressure. And then we have liquids, which are kind of in the middle. And the most important part about these is that gas doesn't have much room for experimentation. There's not much chemistry that can occur within a gas. It's all just bouncing around. It's all crazy. And same with solids. Solids are already the way that they are. You create these crystalline structures and they just stay like that. Like this rock doesn't change much, But liquids are interesting because liquids provide a substrate that then other molecules can come in and they can start interacting in the liquid and start to interact with each other. So that's why liquids are so special. And now let's talk about this special 4th kind of matter, chained matter. And so chained matter starts to happen when you have water molecules. And the question at hand is, when you have all these other elements that get to interact with each other in this way, what kind of natural forms do they fall into? If you think about survival of the fittest, it's kind of like survival of the stable. What stable forms emerge? And what you find is that, something like nitrogen, the nitrogen that's in here, it doesn't form into these chains. Nitrogen doesn't like doing this with each other. It's not going to naturally form into these chains. But something like carbon loves forming little 2-carbon chains, a little 2-carbon chain. These ones might form together to form a 4-carbon chain. And so what you start to get is a bunch of chained matter. These long carbon chains that will sometimes have a little bit of hydrogen on them. They'll sometimes have a little bit of oxygen on them. We're starting to make a glucose molecule here. And so these carbon chains are a natural form of matter that emerges. Carbons require a little bit of energy to form a chain like this, but once they do, it doesn't easily break up. And so you have gas bouncing, solids crystallizing, liquids sloshing, and carbon chains linking. And that's what all of life is, right? All of life are, we're 50% carbon by dry mass. All of our bodies are just these carbon chains interacting with each other in all these different ways. Sometimes you get chains like this. Sometimes you might get a ring, like, boom, we've made a ring. Sometimes you get a ring made of 6, molecules. And so these carbon chains form the building blocks of life. Okay, so now I want to talk about the third part, which is how we actually got these carbon chains, this chained matter at the beginning of life. And we know that once you have some of these carbon chains, they like to stick around, but it's kind of annoying to get them there in the first place. So for example, here's a CO2 molecule. That's a carbon, these are 2 oxygens. And so all of this is in the atmosphere. This is also gets into the water sometimes. We also have this methane molecule. This is a carbon with a bunch of hydrogens. This is CH4. And we know that thing that's in between that, something like this is called formaldehyde, which has a carbon, an oxygen, and 2 hydrogens. So this, almost all of life looks like this. It has carbon and oxygen and hydrogen. These are called hydrocarbons. And so the question is, how do we turn CO2 molecules into carbon chains that look like this, with this ratio of carbon to hydrogen to oxygen, without going all the way to something like methane, CH4? And so the issue is that, if you imagine some of these molecules, if you imagine a couple formaldehydes, these are again formaldehyde, we love the ratio here. This is the ratio of life, has this perfect ratio of carbon to hydrogen to oxygen, but they don't easily mix with each other, right? These two kind of like hanging out with each other, but these two don't like hanging out with each other, and there's no easy way to form chains. And so there are kind of 3 big ways that we think these chains got formed. And so the first way is with this beautiful molecule called hydrogen cyanide, which is dangerous. But, and this is from John Sutherland and colleagues, and the idea is that this is a beautiful molecule. This is a hydrogen with a carbon with a nitrogen on it. And the reason why you like that is because nitrogen is part of the building blocks of the rest of life too. And so if you already have nitrogen here, it can easily be formed into different chains later. And the other reason why we like it is because it's kind of easy for this nitrogen to kind of get pushed away as ammonia, as NH3, and for carbon chains to begin to form. And so there's a whole series on this, but this might be the keystone molecule of life. And this thing easily forms during these big asteroid impacts that were happening during the late heavy bombardment. So this is maybe one way, hydrogen cyanide. The second way to produce, carbon chains is through this process called the Wood-Lungdahl pathway. And that's a part of a more general thing called carbon fixation. And carbon fixation is what happens with photosynthesis. So you can imagine, here's some CO2 molecules, and here's some H2O molecules. And what photosynthesis does is it fixes carbon. It uses, chlorophyll to rip these hydrogens off of the oxygen. It puts it on to here in various ways so that these can start to form these longer carbon chains. It fixes carbon onto itself so that it turns CO2 into long carbon chains like glucose. And then obviously it takes what was H2O, now it takes this oxygen and says, boop, puts that into the world, and then we breathe this later. That's what carbon fixation does with plants, where it takes CO2 and turns it into these carbon chains. The issue is that it's really hard to rip these hydrogens off of oxygen. We had to get chlorophyll to do that, and that was invented billions of years later. And so at the beginning, the question is, how do we take these CO2 molecules and fix them together? And so the key difference is that today we exist in what's called an oxidizing atmosphere, where we have all these oxygen atoms moving around. 20% of our atmosphere is oxygen. And because of that, these things can act, we can breathe it in, and it can run a bunch of energetic processes. But back in the day, we had what was called a reducing atmosphere with all of these, or a reducing environment rather, with all of this H2 around, right? Oxygen, we only got an oxygenated environment after photosynthesis, after 2.5 billion years ago, the great oxygen event that, killed 90% of species. And why were they killed? They were killed because they weren't built for a world full of oxygen. They were built for a world full of hydrogen. All of this hydrogen is what's called a reducing atmosphere or a reducing environment. In a reducing environment, we have this pathway, this Wood-Lundahl pathway, which if you look at LUCA, the last universal common ancestor, this is how it turns carbon into carbon chains. And so what it does is it takes CO2 and it takes H2 and it turns it into this beautiful molecule here, acetate, which is just a 2-carbon molecule. The way I think about this is it's taking 2 1-carbon things and turning it into a 2-carbon thing. And so, I could do this with my little hands here, futzing around with stuff, but you can see how this would happen. And so I think of this as the 2-carbon pathway or the acetate pathway, and it's how most carbons turned into carbon chains at the beginning of life. And the third kind of carbon fixation, or the creation of carbon chains, is through what's called the reverse Krebs cycle, or the reverse carboxylic acid cycle. And so the idea here is that you start with a feedstock of this acetate, of these 2-carbon molecules. You have a bunch of them around, the 2-carbon system is producing lots and lots of this. And then what it does is, I'm going to put a simplified form here. What it does is you have these 2-carbon chains, and then CO2 comes in, CO2 begins to come in, and then it gets added to this to make a 3-carbon chain. And then you have another little CO2 molecule come in, and then another CO2 molecule comes in, it drops off another carbon, it makes another carbon chain, and then another CO2 comes in, drops off another carbon, then another CO2 comes in, drops off another carbon. And before long, what you have is you've taken this little 2-carbon that you've had here, and you turn it into this longer 6-carbon chain. This is called citric acid. This is why it's called the citric acid cycle. And so what this beautiful thing does is it takes 2-carbon chains and it turns them into these 6-carbon chains, and that can even break up and produce more 2-carbon chains. And then you can imagine this autocatalytic loop happening where you're taking a feedstock of 2-carbon chains and you're using it to produce lots of 6-carbon chains, lots of 3-carbon chains, lots of 5-carbon chains. And those chains are, 3, 4, 5, 6. Those underlie all of life. That's where proteins and sugars and everything comes from these 2 through 6 carbon chains. So what you can hopefully see here is that we've moved from the first kind of matter, there's lots of gas, then we saw how solids work and create these long crystals. We saw liquids and how liquids create a substrate for then chained matter. And we saw all these 3 different ways that chained matter might be able to be created in the early Earth. And so in future episodes, we'll show how early life, really proto-life, began to have a survival of the fittest chemical reaction, producing lots and lots of chained matter, and we'll look at the chained matter that starts to exist. Thank you, as always, for watching, and thank you to Roots donors for supporting this channel. If you want to understand more about the past and how we got here, check out the previous videos here. And if you want to understand the future and where we're going, feel free to subscribe here. Hope to see you then. Bye.